Welcome back to ECE 501B. Homework number 7 is getting my classes mixed up. It's due Monday. The exam is a week from today, and we will have a review session. I did hear back that will be in this room after class on Monday. Hopefully I won't get sick this time going into exam number 2, like exam number, I was trying to remember where we had the review lecture. Now I remember. It was probably not very pretty to listen to. I think my voice was a little bit odd. But I have a long list to try to cover today, and it still continues beyond the screen. But here are our goals. One, I want to recap where we've been so that you're comfortable or a little bit more comfortable with self-adjoint operators. I think last time we finished up with showing how we could create those with taking the complex conjugate transpose of a matrix representation of a linear map. So we'll review that, or we'll recap that. Then we will look at, now think back when you were smaller or younger, and maybe you built things or played with things, and maybe you had little toys that you like to play with, build things, maybe Legos, maybe Lincoln Logs, maybe Tinker Toys, maybe in your own country it was something else, but you build up from basic pieces. That's what I want to do with this simple linear map. What is about as simple of a linear map as we can look at, and that's when we have a scalar map or a one-by-one matrix. We'll look at that and see how that allows us to look at certain numbers and how those actually are generalizations, or you can generalize these numbers into certain properties on these maps. What's it mean to have a linear map? What's it mean to have an adjoint? What's it mean to have a self-adjoint linear map in terms of numbers? And we'll illustrate that by means of this simple example. And we'll build up a table to outline that. So if somebody goes, oh, an adjoint, you go, oh, that's just a complex conjugate. I kind of know what that is. Or a self-adjoint, oh, that's a real number in terms of a map. But it's a generalization of that. So now instead of a 1-by-1 relationship, now you maybe have a 10-by-10. But the idea is, oh, that's a linear, or I'm sorry, that's a real number, is the thinking that you could use when you have a self-adjoint map. Then we'll look at several different propositions and corollaries that we can basically state once we are working with self-adjoint maps. We're going to have a lot of different terms floating around. Then we will talk about normal operators. And a normal operator is one in which the linear map and its adjoint commute, meaning it really doesn't matter if we go T and then T dagger, or if we go T dagger and then T, in terms of moving from something to the result. If those are equivalent, if T and T dagger commute, then that operator is called a normal operator. And the fact that we have normal operators allows us to do some pretty powerful techniques in terms of thinking about these maps and what they allow us to do. Wow, I'm still going with my list of topics that I'm trying to cover today. If you have a self-adjoint operator, that immediately is a normal operator. A self-adjoint operator said that T was equal to T dagger. So if you plug in T and T dagger being equal, you can see that T squared is equal to T squared. That makes sense. But if you have a normal operator, it may not be self-adjoint. So you don't have to have a self-adjoint operator to have a normal operator. That's maybe a bigger set. Self-adjoint is more restricted. Then we will talk about, oh, I like just norm and normal. So we don't have any norms in here, do we? name-wise. I have a cousin named Norm, but I don't think anybody in here. So I'm going to be talking or deal with norms and normal operators. And if an operator is normal, then the norm of TV is equivalent to or equal to the norm of the adjoint of T with V. So that's an if and only if relationship. If you can show that these norms are equal, you know now that your operator T is a normal operator. That's another way of coming up with a normal operator. Then we will look at the relationship between a linear map T and its adjoints, eigenvectors, and eigenvalues. We'll show that if T has an eigenvalue lambda and an eigenvector V, its adjoint has the same eigenvector V, but its eigenvalue is lambda star, the complex conjugate of the original eigenvalue. So we'll look at a result dealing with the eigenvalues and eigenvectors of a map and its adjoint. Then we'll keep going and we'll look at normal operators that have distinct eigenvalues. And in those conditions, those eigenvectors associated with those distinct eigenvalues will actually be orthogonal. And we know that orthogonal vectors are nice, aren't they? They allow us to do many more useful things. And when are we able to talk about orthogonality? When we have an inner product, when we can show things are orthogonal. So that's why we're playing now on this inner product space, chapter 6. Now we're playing with operators on that, and we'll get into spectral theory. Basically, can you diagonalize operators? Or do the matrix representations of these maps, can they be represented as diagonal matrices? And it depends on whether we're dealing with complex inner product spaces or real inner product spaces, and so we have to sort of look at those differently. All right, I'm done. Oh, we need to do this, don't we? So that's our goal, is to work through these. Let's now recap the self-adjoint concept that we began chapter 7 with. And a self-adjoint is an operator. But if we had a linear map, and here I'm dealing with a 2 by 2, not a 3 by 3, but hopefully you can see that this linear map gives rise to the following matrix representation. It's ax plus by in the first coordinate, ax plus by, and in the second coordinate, it's cx plus dy. Is everybody okay with that map T and its matrix representation? And the notation that we've been using in the textbook is, and that's supposed to be a script M. My writing maybe is not as clean or neat as yours, but that's script M of square bracket T, where T is the linear map. Now, we defined self-adjoint operators before, but first let's just find the adjoint. We haven't yet said anything about whether T and T dagger are adjoints or not. I'm sorry, or if T is a self-adjoint operator. So let's just first find the matrix representation of the adjoint of T. And that last time we said is the complex conjugate transpose of the matrix representation for T. And we can do that pretty easily. We can transpose a 2 by 2. We don't do anything with the diagonal. We just flip the off diagonals, and now we conjugate everything. And that's hopefully what this represents. But now that we have this matrix representation of the adjoint, can you now write down the linear map of that adjoint? Based on what we did, we went from the linear map to the matrix. Now, once we have the matrix, you can immediately write down the linear map of the adjoint, I hope. this matrix representation says take A star times X and add to that C star times Y. And that's going to be the first coordinate of the result of taking the adjoint of T applied to XY. Likewise, if we take B star plus X plus D star times Y, that's our second coordinate in this linear map that's representing the adjoint of the first or the original linear map T. Meaning you should be comfortable now sort of going back and forth between this notation for T as a linear map and its matrix representation. Because you may be wanting to do the matrix representation in MATLAB numerically to be computing or playing with all of these operations or these concepts that we're discussing. Self-adjoint, that means that T is equal to T dagger if the map is a self-adjoint map. Meaning if we applied that condition, meaning if we wanted T, the original linear map, to be a self-adjoint operator, then we would need to equate the two entries in the two 2x2 matrices, which says that the diagonal terms have to be equal. A is equal to A star, where star is the complex conjugate. D is equal to its complex conjugate, and the only way that can happen is for D, for it to be a real number in order for it to equal its complex conjugate. Similarly, the off-diagonal terms need to be related by a complex conjugate operation. B needs to be equal to C star, and C needs to be equal to B star. But if B is equal to C star, you know that C is equal to B star. So you just need to sort of make that relationship true for one of these, and then you have it for the other. But if we simply blindly equate all four entries, that is the relation, that's the set of relationships that we would end up with. What's that then say about the general form of a self-adjoint operator? This is maybe a busy matrix, but sort of just watch it and take it all in. Meaning, we need the diagonal entries to be real. So the A11, the A22, the A33 through ANN, those are all real. And then we have this complex conjugate relationship between the off diagonals. Meaning the top half, or the top above the diagonal, I simply labeled as A12, A13, etc. And then I simply took the transpose of those and conjugated those and put those in the appropriate location below the diagonal. And that's now the general structure of a self-adjoint operator. And you can start to think about a self-adjoint operator if you were dealing with a real inner product space. Then you don't have to worry about the conjugate operation, and you now know that A12 is equal to A21. A13 is equal to A31, etc. Or A sub 7, 8 is equal to A of 8, 7 in an 8 by 8 matrix. Questions on that? That's just the generic structure of a self-adjoint operation, and that's the matrix representation of that linear map. And this structure being a complex conjugate transpose is going to hold no matter what basis you have for that linear map. And finally, on the note, a maybe very straightforward self-adjoint matrix representation would simply be a purely diagonal matrix. As long as what? Those diagonal elements are real. If you have a diagonal matrix with all real numbers on the diagonal, that's a self-adjoint matrix. It doesn't have to be diagonal, but that makes for a easy, cleaner thing to deal with. That would be a self-adjoint matrix. That's our recap. Now what I want to do is slow down a little bit. That was our movie that you just sort of sat back and watched, maybe, and the notes will be available if you want those, if you weren't quite fast enough to go through while I was scrolling. Now let's examine a simple map and see how that simple map generalizes to some of these concepts that we're dealing with in terms of a linear map, the adjoint of that linear map, and if a linear map is self-adjoint. What we want to do now is look at a simple example. So I'll write this down and then try to show it symbolically. A simple example showing that the matrix representation of an adjoint is the complex conjugate transpose of the original map, where the original map is T. Or maybe more symbolically, what I'm saying is we want to look at the matrix representation of T dagger, and we want to see that that is equal to the matrix representation of the original map, complex conjugate, and then transposed. So here's our example. And as advertised, I said that we would look at something very basic. Think about what you did when you were little. You built something big out of something sort of small. And that's what we want to, that's the idea that we're trying to use now. Suppose we have a linear map, T, that's taking a complex inner product space, C, into another one-dimensional complex inner product space, C. We have a linear map from C to C. I feel like I should be singing from C to shining sea. No, that's different C, isn't it? Maybe that doesn't make any sense to most of you, but never mind. What is a linear map that will do that? Well, we have this convention. Now I have one coordinate, and that coordinate is x. So T applied to x is going to give me AX, where A is in our field, but let's go ahead and let that field be the set of complex numbers, or this complex space, and X is also in the same field of numbers, complex numbers. You could think of A, and this is what a lot of times students get a little bit uncomfortable with, but A is a matrix, isn't it? It's a one-by-one matrix. A is a scalar, but you could also think of it as a one-by-one matrix. A is complex, but A is a scalar, but yet you could think of it as a one-by-one matrix. It's a complex scalar, or it's a complex one-by-one matrix. Which then says that the matrix representation of this linear map T, which we symbolize by saying script M of square bracket T, is just A, where A is this one-by-one matrix. Now, what we are trying to do is, if A is a complex number, that's our linear map, we now want to think about these other possible maps. And one that we've talked about is the adjoint map. So what's it look like in terms of a number, maybe, a matrix? We want to know what's the matrix representation of the adjoint of T. And then we might say, what's that mean if we talk about a self-adjoint map? What's that look like in terms of a matrix, a one-by-one matrix? Let's apply then the definition of the adjoint to see what the matrix representation of the adjoint of this one-by-one matrix looks like. And again, I'm hoping that going through this will give you something to sort of rest on or reflect on or think about when you're reading the text, and all of these terms and definitions and propositions are flying around and you're going, I don't know, the adjoint is this and the self-adjoint means this. This you can just sort of go back to and say, oh, that's what this means. If I boil it down or distill that down to the simplest possible case. What's the definition of an adjoint? That was by means of inner products, wasn't it? You could say that if we had T applied to a vector X, inner product with V, by the definition of the adjoint, what's that equal to? That inner product needs to be equal to X, inner product, so in the second slot of our inner product, it's the adjoint of T times V. Is that okay? And now we have this T being a one-dimensional linear map. And we want to apply that and see what that means in terms of what T dagger or the adjoint is going to end up looking like. If we apply the Euclidean inner product, which in this case are coordinates, we only have one coordinate, so that's pretty easy. We just have to multiply things together. But now we have T applied to X times the complex conjugate of the second slot, which in this case is V star. That's equal to X, the first slot, times the complex conjugate of the vector in the second slot. And the vector in the second slot is this operator or linear map T dagger applied to V. We don't know what T dagger is, but we do know what Tx looks like. Didn't we define that? Tx is just Ax, like what we've been playing with before. Well, if the adjoint is a linear map, we know it has to look like maybe BV, some B, some scalar times the vector that it's applied to. Meaning, if Tx V star is equal to X times the complex conjugate of T dagger V, that means that we have Ax V star, that's on the left. That's just using the definition of our linear map for T. And that's equal to X. Well, we don't know what T dagger looks like, so let's just create a new variable. We'll call it B since we've used A. Let's say that this is BV complex conjugate. This is now, this B is an unknown scalar, or a yet to be determined scalar. We haven't yet determined what that is, but now we know really what that's going to be. We can now say that if B is a scalar, X is a scalar, V is a scalar, we can apply the conjugate to those scalars, and we have X, B conjugate, V conjugate. And since those are all three scalars, they commute, they're complex numbers, so A times B is the same as B times A. We can say that B star, and you can make better stars than I can make. That's not difficult, is it? That's an easy task. This is now X V star. But here's X V star, and there's X V star on the right. So that says that whatever that B was, its complex conjugate needs to equal A. Or B, if I complex conjugate both sides, is equal to A star. And what's that going to, what does that tell me? B was what I said the adjoint was as an operator. So that's now telling me that if I have the adjoint operating on a vector V, where V is just a scalar, that's now equal to BV, but B we found in terms of the original map, which was A star V. And now we know what the matrix representation of that adjoint operator is. That's A star. That's the complex conjugate of the original linear maps matrix representation, which was A. A star is a 1-by-1 matrix. We said T as a map was just A. Its adjoint now is its complex conjugate. We derived that from the definition of the adjoint. That was our inner product. That allowed us to get to this point. Because you're going to see when you're reading some of this that people will say, oh, well, the adjoint is just the generalization of the complex conjugate. Well, now you know where that's coming from. Let me write that down. Therefore, the adjoint of a map is the generalization of the complex conjugate of a complex number. Meaning if we start with a complex number and take its complex conjugate, that's the same as starting with a linear map and finding its adjoint. That's sort of the concept or the idea. And again, this was the building block. This was the basic. This is as easy as it gets. That's a one-by-one matrix. What if we had an operator that was self-adjoint? We've just now found what a map and its adjoint look like, the relationship between those in terms of the simplest case. What about a self-adjoint operator? What's it mean for an operator to be self-adjoint? It has to be equal to itself. The adjoint has to be equal to itself. That means T is equal to T dagger. That's self-adjoint. That means itself is equal to its adjoint. That says then that T is equal to T dagger. But what did we just learn about an operator or a map T and its adjoint? They were related by a complex conjugate, weren't they? So now we're saying that A must equal to A star, where A now is a complex number. But it can't be. It can't have an imaginary part. It can be a complex number. A real number is a complex number. It just has a zero imaginary part. So this now says that A needs to be real. That's what a self-adjoint operator looks like, is a real number. So now if somebody is saying, oh, I have a self-adjoint operator, you can sort of say, oh, in a one-by-one case, that's just a real number that scales the vector that he's working with. Not too hard, is it? But the self-adjoint makes it think like, whoa, wait a minute, where are we? But these are okay concepts to deal with. Let's now build a table of what we've just concluded. Suppose I make one side of this table a number, and the right-hand side, I'm going to say generalizes to a particular map. Meaning, what if I said first, I have just a generic number, and now I'm maybe over abusing notation. But suppose A and B are real numbers, and now my complex number Z is A plus JB. So I'm explicitly identifying the complex part. So this is now Z is a complex number. That is consistent with a generic linear map T. I might as well make my table look consistent. What if I now took the complex conjugate of Z? That's now A minus JB. What do we know that looks like in terms of the linear map T? That's the adjoint map, isn't it? Meaning if you're starting to feel like you're going into the deep end and you're starting to sink, you can just go back to this table and say, wait a minute, an adjoint, let me just think about the complex conjugate in terms of concepts. Then what about if Z was just a real number? Then we know that this map T is in fact a self-adjoint map. And so these are sort of the simplifications that you can think of or keep in mind when somebody starts talking about a linear map, the adjoint of that linear map, and maybe that map is self-adjoint. And keep that in mind when we're working through Chapter 7. Now what we want to do is work through or state and derive some propositions or prove some of these, and we won't prove all of them, we'll just prove some. Propositions and corollaries that are associated with these maps on inner product spaces, and typically complex inner product spaces. Let's look at the first one. Proposition 7.1. Wow, that's appropriate. First proposition in Chapter 7. Chapter 7 starts with talking about an operator being self-adjoint, and now you have a feel for what that means. Every eigenvalue of a self-adjoint operator is real. Wow. So now if you know you have a self-adjoint operator, and if somebody said, what are the eigenvalues, you already know they're all real. And T, the linear map, could be a 10 by 10. You know you have 10 real eigenvalues. That's what this is saying. So that self-adjoint is a powerful descriptor for a linear map. Let's prove that, since it's not too big of a deal to prove. Proof. Suppose we now have this linear map in the set of linear maps on a vector space V, and we are told, we're given the fact that T is equal to its adjoint. Those are the facts in this proposition. Next, let's just assign some variables or values to this in the form of, let's suppose that we have the following eigenvalue eigenvector relationship for the linear map T. Lambda and V are the eigenvalue and eigenvector of this linear map T. Now let's play with some of these terms that we know how to play with. Suppose I say lambda times the norm squared of V. I can rewrite that as, what's the norm squared of V equal to? The inner product of V with itself, and I can put that lambda into the first slot without any modification. So this first step is really just the definition of the norm and the homogeneity of the first slot. So that wasn't tough, that first step in our justification, or what are we trying to prove? That all these eigenvalues are real. So here, that's our first step. The next step, oh boy, that's just screaming at us, isn't it? We have lambda v. Well, we know what lambda v is equal to. That's TV. We like TV, right? Oh, not television, but the map T applied to the vector v. So with the using the eigenvalue equation, eigenvalue, eigenvector, well, let me just say eigenvalue equation or eigen equation. Maybe that'll be better. We get that lambda, the norm of v squared, is equal to the inner product of TV with v. But then we can move that t to the second slot by using the definition of the adjoint, which says that if I did that, what does the next line look like? This is now v, t dagger v, isn't it? But now, whoops, it's off the screen, but we assumed t was self-adjoint. So t is equal to t dagger. So we wouldn't have even had to do this step, but I'm including all the steps. We can now say, and you know, if you were writing this in a paper, you'd probably skip most of these steps and you'd just say lambda norm squared of v is equal to the result, which is where we're going. And you would say it's intuitively clear, or it's obvious, right? With your maturity now, knowing how these steps go, you would know all of this and you would just erase it, write that down and say, it's immediately clear that these are real. Maybe you wouldn't even say, here's the proof. You would just say, proof is obvious, right? All right, so that's where we're headed by the end of this semester. But knowing that this is self-adjoint, we can write that. Bless you. And now what do we do? Well, we just use TV again. We know that that's equal to v lambda v. But what happens when we pull that lambda out of the second slot from the inner product? That's the complex conjugate homogeneity of the second slot, isn't it? So this is now lambda star v v, or the conjugate homogeneity of the second slot. And then we can clean that up and we can say, well, that's just lambda star times v squared, or the norm of v squared. Whoops, don't have a big enough screen. My TV's not big enough. My lambda v's not big enough. And we know what I'm talking about, right? Or maybe I should say monitor, and then that kind of loses some of the cuteness of that result. What did we start with? We said that lambda v squared is equal to, and now we derived down and we ended up with, well, did we just get back where we started? Not quite. There's a lot of power in that equality. We've just shown that lambda v squared is equal to lambda star v squared, but v squared is, for a non-trivial vector v, we can say that that's not equal to 0, and it's positive. We can divide that out, and now we get lambda is equal to lambda star. And what's that say? Well, for a complex number to equal its complex conjugate, it has to be real. And that's what we were trying to show. Yes? That was, so the question was, how did we know it was self-adjoint? That was our hypothesis. We were given that. So we don't know. You have to be told. If you now have a self-adjoint operator, then you know every eigenvalue is real. But you have to then show that you have a self-adjoint operator. This theorem is just saying, given that, if your operator is self-adjoint, then every eigenvalue is real. Then you can apply proposition 7.1 if you know your operator is self-adjoint. So we were assuming that to be the case. And did I write down the conclusion? Therefore, all eigenvalues are real. Let's now state several propositions and corollaries dealing with these concepts. So now let's look at several propositions and corollaries from the textbook. And now that we've seen one proof, I'm assuming you can sort of read those on your own. We need to move. That was just the first proof or proposition in chapter 7. We don't have that much time, do we? We can't spend that much time on all 50 propositions in the chapter. I don't know how many there are. That's your assignment for tonight. So see the text for some of these proofs. First, let's look at proposition 7.2. If V is a CIPS, does everybody know what that means? A complex inner product space, and that's important that it's complex. It can't be real. It's complex. And maybe I'll ask you a week from today, why is this not true for a chapter 7's not on the test, is it? Oh. All right, so if V is a complex inner product space and we have a linear map T on V, so we write that by T as an element of script L of V, such that the inner product of TV with V is equal to 0 for all vectors in the complex inner product space V, then that linear map is actually 0. So if we have a situation where this linear map T applied to every vector in V, inner product with every vector in V is 0, then we can conclude that that map was actually 0. What's another result? Corollary 7.3. If V is a complex inner product space, and T is a linear map on that complex inner product space, then T is self-adjoint, and you were asking, is our operator self-adjoint, or how did we know that? Now we have a way of determining that. This linear map is self-adjoint if and only if the inner product of TV with V is a real number. It's not complex, and that's true for all V in our complex inner product space, capital V. So if we can find that the inner product of our linear map with a vector V and V itself is always giving us a real number, then that T is self-adjoint. Or we can go the other way. If we know that our map is already self-adjoint, we know that its inner product, TV with V, is going to give us a real number. It won't be complex. Again, think of these in terms of the simplest case, where T is a 1-by-1 linear map. I said we'd be stepping through these quickly. Proposition 4 in Chapter 7. And this really is going to generalize Proposition 7.2. If T is a self-adjoint operator on V, so now that's what? Like a real number in a 1-by-1 case. If T is a self-adjoint operator on V such that TV inner product with V is equal to 0 for all V in the complex vector space V, then that linear map is 0. In Proposition 7.2, we didn't have this T being restricted to being a self-adjoint operator, but we needed T to live in a complex inner product space. In Proposition 7.4, we're not saying where V is, are we? V could be a real inner product space or a complex inner product space, but we need T to be self-adjoint, which is a linear map. That's like having a real number as our operator on that linear map. Meaning this proposition extends Proposition 7.2 to RIPS, but this one adds the requirement that we need that operator to be self-adjoint, but adds requirement of self-adjoint operator. So now we have some things to play with relative to these self-adjoint operators that was sort of the first definition in Chapter 7. Now let's define a new operator, which we're going to call a normal operator. Normal operators. A normal operator on an inner product space, I'm not restricting to be complex or real, a normal operator on an inner product space is one where T commutes with its adjoint. I.e., T times T dagger is the same as T dagger T, which means that if you are moving between some vector space and another inner product space via two maps, it doesn't matter how the order in which you apply those two maps. You could first apply T and then the adjoint, or you could go back to your starting vector and apply the adjoint and then T, and you get to the same spot. Or those maps behave the same. Doesn't really matter the order with which you apply them. Wow, I'm skipping a lot of notes, huh? So now let's just write down some facts. First, all self-adjoint operators are normal. Since T is equal to T dagger, T times T dagger is equal to T times T, which is equal to T dagger T, or T squared. So you're just repeating that map twice is really what that would be saying if you needed to show that T dagger is T dagger T. Well, they're both TT if T is self-adjoint. Now we can't go the other way. So that's one result. Normal operators can include, this is sort of a weird way of maybe saying this, but non-self-adjoint operators. Meaning you can have normal operators that are not self-adjoint. Self-adjoint is more restrictive than normal. So normal operators can include non-self-adjoint operators. And Axler gives us some examples, or one example. So let's look at that. Axler gives example of T with the following matrix representation. Suppose that now we have the following linear map. Matrix representation is 2 minus 3, ooh boy, 3, 2. Is that matrix representation self-adjoint? First, it's real, isn't it? So we don't have to worry about the complex conjugate business. But this has to equal its transpose to be self-adjoint, and it doesn't, does it? If we transpose this, we would get minus 3, 3, and that's not the same matrix. This matrix, then, is not self-adjoint. Now, I could, a week from today, ask you, okay, here's the So here's sort of a review. This is sort of an aside, but if this is the matrix representation of a linear map T, what is the linear map T? If I said here is T of xy, give me the coordinates, the resulting coordinates of T operating on xy. First, how many coordinates do I have? This matrix representation is square, so I'm only going to have the same number of coordinates that I start with, and here I'm saying I'm in what? I'm on the floor, aren't I? I'm in the xy plane. What's the description of the first coordinate of the output of this linear map? Does everybody see that? So now I could give you a linear map and say, what's the matrix representation? And you can do that in your sleep now, right? What's the second coordinate? Three x plus 2y. Now, what's the matrix? So that was sort of an aside, but you can, that's sort of a review question. What's the matrix representation of the adjoint of T? If we know what the matrix representation of T is, how do we get its adjoints matrix representation? Again, it's easier because it's real, isn't it? These are real numbers. We could still be in the complex field. We just have a map that's all real. So we can complex conjugate that, and it gives us the same matrix back. But now if we transpose it, we get an error. There is our matrix representation of the adjoint of that operator, T. And I guess I could say, what's T dagger for completeness? And now you can sort of start maybe looking at these linear maps and saying, are they adjoints? Yes, they're adjoints. Are they self-adjoint? Does this 2, 3 minus 3, 2 equal 2 minus 3, 3, 2? No. So we know they're not self-adjoint, but is this linear map normal? So now what do we need to show? I'm kind of getting lazy. Let me call this A, and can I call this B? I need to show that AB is equal to BA, right? So now what's AB? AB was 2 minus 3, 3, 2, and B was 2, 3 minus 3, 2. The 1, 1 entry is going to be 4 plus 9, or 13. The 1, 2 entry, if I take, or let me do the 2, 1 entry, I take 3 times 2 and add to 2 minus 3, it's 6 minus 6, that's going to be 0. If I look at the 1, 2 entry, I have again 6 minus 6. And if I look at the 2, 2 entry, I have 9 plus 4, or 13. Now if I look at BA, does the map and its adjoint commute? That's what I'm checking. This is now 2, 3 minus 3, 2 times 2 minus 3, 3, 2. And again, I get on the diagonal, I get 4 plus 9. The off diagonals, I get zeros, don't I? 6 minus 6. So now in this case, this matrix A, which, let me go ahead and define that as, or write that down as I had defined A, which was 2 minus 3. Wow. I told you, watch my battery pack and see if it turns red. Me, just see if I turn ghost white, and then I'm out of energy, okay? I'm out of energy. There's many mistakes as I'm making, but now A is this. That's not self-adjoint, is it? Is not self-adjoint, but 2 minus 3, 3, 2 is a normal operator. So now if you went back up to these, to this T, it may not be obvious by looking at that T, but now you can say that T is a normal operator after looking and comparing whether T and its adjoint commuted. Now the next proposition gives us another way of checking whether or not a map is normal. But that's just a quick example of how a normal operator doesn't have to be self-adjoint. But every self-adjoint operator is normal. Here's proposition 6 in chapter 7. An operator T that's mapping between these vector spaces V is normal if and only if the norm of TV is equal to the norm of T dagger V. So now if you have an operator, T, and you compute its adjoint, which now you kind of know how to do that, and you find that their norms are equal, well, you probably need to make sure that that's true for all V in the vector space V, but if it is, then your operator T is normal. Okay? So let's prove that. We haven't proved anything for a little bit. Let's look at the proof. If T is normal, that's true, let's say, if and only if they commute, right? Well, we can write that as T dagger minus T dagger T is equal to 0. But now we know how we can write that in terms of an inner product. For all vectors V in our vector space, we can have the inner product of 0 with V. But we'll write 0 in this nice way. 0 is 3 minus 3, right? Well, now it's T dagger minus T dagger T. That's also 0. So let's now take the inner product of 0 with V for all V in capital V. Whoops. Sorry. What was I doing? besides being crazy. We now have T dagger, and I don't know why, but my notes now I've reviewed, or let me change this. Can I change this first line so that it's going to be more consistent with my notes? Wow, it's wanting to fall asleep too. So now let me say that this is going to be T dagger T minus T dagger, because I want my dagger there. T dagger minus T dagger, that's 0, with V is equal to 0 for all V. Is that okay? So T dagger T minus T dagger is 0. T commutes with its adjoint. Now let me use that 0 in an inner product with V. Well, now let me apply the linearity in the first slot of the inner product. Which now allows me to say, whoops, what am I doing? I told you I was falling asleep. You were looking at that kind of weird and saying, how can you do an operator with an inner product? It has to be a vector, doesn't it? So I need to squeeze a vector in here like that. Is that okay? Is that better? It's better than it was. So now I have a vector inner product with a vector, and that vector now is 0 with V. I was getting so hung up on 0, but I can take 0 as an operator and operate it on V and still get 0. Now I can do the linearity of the first slot, and I can say that T dagger T V, comma V, minus T dagger V V is still equal to 0 for all V in my inner product space, capital V. But now I can simply add one of those to the other side, or add one to both sides to get them on either side of the equality. That is equivalent to T dagger T V V is equal to T dagger V with V. And now what I want to do is go back and apply my definition of the adjoint on just a little piece of that. Meaning, let me just apply the definition of the adjoint to this one operator of the two that are combined. Do you see what I'm doing with my parentheses now? On the left side, I want to apply my definition of the adjoint to this inner product. And on the right side, I want to do it to the other inner product. Meaning, by the definition of the adjoint, what do I have on the left-hand side? I want to take the adjoint of the adjoint and put it in the second slot. So that now I have TV with TV. Is that okay? Which really, what I've done, maybe to do it more in more steps, I've done T dagger V. And this one on the right-hand side is now T dagger V with T dagger V. And this guy, I think we talked about that last time. That's just T, isn't it? When we take the adjoint of the adjoint, that's simply T. So that now I have, on the left-hand side, I have TV with TV. And on the right-hand side, I have T dagger V with T dagger V. And again, this is true for all V. But what is that on the left? That's the norm squared of TV, isn't it? What's on the right? The norm squared of T dagger V. And they're equal for all V. And isn't that, bless you, and that's what I wanted to show, wasn't it? Because I really have this if and only if in each of these steps. I could go in either direction. So I've sort of proved the if and only if in all of these lines in both directions, left and right. Now what I should have you do for an exercise is verify the following. That T dagger T minus T dagger is self-adjoint. What does that mean? If you needed to prove this, you could say, well, just what if I take the adjoint of that mess? And if that ends up being equal to that mess, then it's self-adjoint. And we'll stop at that point and pick up Monday in chapter 7.